before the ground moved, before concrete cracked and steel screamed, the argument had already begun. It started quietly inside a conference hall thousands of miles from the Philippines, where a respected Japanese seismic expert stared at a set of architectural drawings and shook his head. The design, he said, looked fragile, improvised, too dependent on assumptions. In a region sitting on the Pacific Ring of Fire, assumptions could be deadly. The Filipino engineer who submitted it listened in silence. He knew something the room did not. He had built this house for an earthquake that had not happened yet. The Philippines is no stranger to seismic violence. Entire neighborhoods have learned to live with the possibility that the earth beneath them could betray them without warning. Yet most homes remain ordinary, built quickly, often under financial pressure, and rarely designed with catastrophic earthquakes in mind. Against this backdrop, one experimental house stood out, not because it was tall or futuristic, but because it rejected almost everything modern earthquake engineering usually prioritizes. Its designer claimed it would survive forces that should have destroyed it. That claim would soon be tested. The designer, a mid-career Filipino structural engineer named Rafael Alonzo, did not come from prestige institutions. He grew up watching houses collapse during typhoons and tremors in provincial towns. Concrete walls cracked, roofs slid off, people rebuilt the same way, again and again. Rafael believed the problem wasn't just materials, but philosophy. Earthquake-resistant design, he argued, had become obsessed with resisting motion instead of accepting it. His house was not meant to fight earthquakes. It was meant to move with them. When Rafael presented his concept at an international seismic safety symposium in Osaka, the audience listened politely. His slide showed a modest, single-family home elevated on a layered base of timber, rubber composites, and steel joints. There were no massive shear walls, no dramatic dampers. Instead, the structure rested on a controlled flexibility system inspired partly by traditional Filipino stilt houses and partly by earthquake-isolated temples in Southeast Asia. The Japanese expert in the front row, Professor Hiroshi Tanaka, was unconvinced. Professor Tanaka was not easily dismissed. He had spent 3 decades studying earthquake failures across Japan, from Kobe to Tohoku. His career was built on data, not intuition. As Rafael spoke, Tanaka circled sections of the design with a red pen. Too much reliance on wood, insufficient lateral bracing, excessive movement tolerance. When questions opened, Tanaka's voice was calm but firm. In a major seismic event, he said, "This house will experience displacements beyond safe limits. Occupants would not survive." The room nodded. Japan's seismic standards were among the strictest in the world. If Professor Tanaka questioned the design, it mattered. Rafael responded carefully. He did not argue numbers. Instead, he spoke about energy paths, about redirecting seismic forces rather than absorbing them, about designing for controlled damage instead of rigid survival. The house, he said, was not meant to look intact after an earthquake. It was meant to remain standing, stable, and habitable. The difference, he believed, was everything. The discussion ended without resolution. Tanaka remained skeptical. Rafael returned to the Philippines with no funding offers, no international endorsements, and a quiet sense of isolation. Yet construction had already begun. On a modest plot of land outside Davao, Rafael was overseeing the completion of the house himself. It was not a prototype for a corporation or a government pilot. It was a real home intended for a real family. Every joint, every layer, every bolt had been placed deliberately. The house did not look impressive. From the outside, it resembled a reinforced rural home, slightly elevated, with wide eaves and thick columns. Neighbors assumed it was overbuilt, maybe even wasteful. They did not see the hidden systems beneath the floor. Sliding plates designed to decouple ground motion, flexible utility connections, sacrificial panels meant to crack before structural failure occurred. Rafael visited the site daily, documenting everything. He was not waiting to be proven right. He was waiting to be proven useful. Months passed. The conference faded into memory. Professor Tanaka returned to his research, occasionally referencing Rafael's presentation as an example of well-intentioned but risky design. In the Philippines, life continued as usual. Then, Early one morning, seismic sensors across the region detected something different. A deep rupture had begun offshore. Within minutes, alerts spread. A powerful earthquake was moving toward the southern Philippines. Its magnitude would later be measured as one of the strongest in the region in decades. The ground shook violently. Roads fractured. Power lines fell. Concrete homes, built rigid and heavy, absorbed forces they were never designed to handle. Walls cracked. Roofs collapsed. Entire blocks were reduced to debris. Emergency responders were overwhelmed. Communication networks struggled. Amid the chaos, Raphael's experimental house was directly in the earthquake's path. Neighbors ran outside, expecting to see it fail. Instead, they watched something unfamiliar. The house moved, not violently, not chaotically. It swayed. Inside the house, furniture slid but did not topple. The floor shifted laterally by centimeters, exactly as designed. Cracking sounds echoed as sacrificial elements broke, releasing energy. Windows flexed within their frames. The structure groaned, but it did not resist the motion. It accepted it. When the shaking stopped, dust filled the air across the neighborhood. People emerged cautiously. Some homes were partially destroyed. Others were uninhabitable. Raphael's house remained upright. From the outside, damage was visible. Panels had cracked. Exterior finishes were broken. The house looked wounded. But when inspectors arrived, they found something unexpected. The main structural frame was intact. Load pads were preserved. Foundations had not fractured. Utilities were still connected. The house was safe to enter. In a disaster zone filled with red tags and evacuations, one small building was declared immediately habitable. The news spread quickly, first locally, then nationally. Video footage circulated online. Side-by-side comparisons showed collapsed concrete homes next to Raphael's damaged but standing structure. Engineers debated the results. Some called it luck. Others called it coincidence. But seismic data told a clearer story. Sensors installed beneath the house showed reduced acceleration transfer compared to neighboring buildings. The flexible base had done exactly what Raphael predicted. It had redirected destructive forces away from the superstructure. The earthquake had tested the theory in the harshest possible way. Across the sea, Professor Tanaka received the footage. At first, he assumed it was incomplete. Then he requested the raw data, waveforms, ground motion records, structural response graphs. What he saw challenged assumptions he had held for years. The displacements were high but controlled. Energy dissipation occurred through intentional damage, not catastrophic failure. The house had not defied seismic physics. It had exploited a different interpretation of them. Tanaka did not issue a public apology. He did not need to. Instead, he contacted Raphael directly. The message was short and formal. He requested full documentation of the design and performance. Raphael responded with everything he had: drawings, calculations, construction logs. The correspondence that followed was technical, precise, and unusually candid. Two engineers from different worlds were now analyzing the same event, from opposite perspectives, without ego. The story gained international attention, though cautiously. Media outlets framed it as a clash between tradition and expertise. But the truth was quieter. This was not about one expert being wrong. It was about context. Japanese seismic standards were built for dense urban environments, high-rise structures, and economic resilience. Raphael's design addressed a different problem: affordable survivability for low-rise homes in developing regions. The earthquake had exposed a gap in global engineering priorities. Investigations continued. Independent teams inspected the house months later. Repairs were simple and inexpensive. Panels were replaced. Connections were reset. The structure itself remained unchanged. By contrast, many conventional homes required complete rebuilding. For families who had lost everything, the difference was devastating. Raphael began receiving messages from local builders, community leaders, and NGOs. They did not ask about awards. They asked one question: could this be replicated? Raphael was cautious. He never claimed the design was universal. Soil conditions mattered. Craftsmanship mattered, maintenance mattered, but the core philosophy, he argued, was adaptable. Designing for controlled movement, intentional damage, and rapid recovery could transform how vulnerable communities approach construction. The earthquake had not validated product. It had validated a way of thinking, one that accepted uncertainty instead of pretending it could be eliminated. Professor Tanaka eventually published a technical commentary. It did not praise the design unconditionally. It acknowledged limitations, risks, and unanswered questions, but also recognized the empirical results. In seismic engineering, real-world performance matters more than simulations. The Filipino house had survived where others had failed. That fact could not be ignored. Quietly, Tanaka included the case study in his graduate seminars. The house itself became a reference point. Students visited, engineers measured, policymakers asked questions. It remained an ordinary home, lived in by a family who had weathered something extraordinary. Children played in rooms that had moved with the earth and remained standing. For them, the design debate was irrelevant. What mattered was that they had not lost their home. That reality carried more weight than any conference argument. Years later, updated versions of the design began appearing in coastal and seismic regions across Southeast Asia. Not identical, but inspired. Flexible bases, sacrificial elements, acceptance of damage as a survival strategy. None of these ideas were entirely new. What was new was their validation under real conditions. The earthquake had provided something simulations could not: proof under pressure. The friction between Raphael and Tanaka never fully disappeared. They continued to disagree on many technical points. But the tone had changed. The questioning became collaborative. The skepticism became constructive. In private conversations, Tanaka admitted something rare in his field. The earthquake had reminded him that expertise must remain adaptable, that models, no matter how refined, must answer to reality. For Raphael, the experience was sobering. He did not see himself as vindicated. He saw the cost of failure all around him: the collapsed homes, the displaced families, the slow rebuilding. His house had survived, but the system around it had not. Innovation, he realized, mattered only if it could reach those who needed it most. Otherwise, it was just another case study. The story of the house was never about proving someone wrong. It was about what happens when ideas are tested outside controlled environments, when theory meets chaos, when the ground moves and assumptions are stripped away. The Japanese expert had questioned the design for good reasons. The Filipino engineer had built it for better ones. The earthquake had been the final, impartial judge. Today, the house still stands. Its scars are visible, intentionally preserved. Cracks that tell a story. Joints that moved and returned. It is not perfect. It is not invincible. But it represents something rare in disaster engineering: humility, an acknowledgement that survival does not always look clean, and safety does not always look rigid. In a world facing increasing seismic risk, climate instability, and rapid urbanization, the lessons from one modest Filipino house resonate far beyond its walls. They challenge the idea that expertise flows in one direction. They question whose standards matter and they suggest that sometimes the most resilient designs come not from the centers of authority, but from the edges of necessity. The earthquake did not announce itself as a test. It did not care about credentials or reputations. It simply applied force. What remained standing was not the most expensive structure or the most complex, but the one designed with failure in mind. That distinction is subtle but profound. For Professor Tanaka, the house became a reminder he shared quietly with students. For Raphael, it became a responsibility he continues to carry. For the family who lives there, it is simply home, a place that moved when the earth moved and stayed when it mattered most. This story, like many told in the aftermath of disaster, blurs the line between innovation and survival. It shows how questioning authority can coexist with respecting it, how skepticism can sharpen ideas rather than silence them, and how reality, when it finally arrives, has a way of cutting through every argument. This documentary-style narrative is a work of fiction created for educational and storytelling purposes. While inspired by real seismic principles and global engineering challenges, all characters, events, and specific outcomes are fictional. The story reflects broader truths about resilience, innovation, and the unpredictable nature of the forces beneath our feet.